Assalamu alaikum, everybody. In the last set of lectures, we discussed about trees generally, and then we concentrated specifically on binary search trees. In this lecture and the next, we will be talking about balanced trees. Yeah, so what is the outline of the topics? First, we will take a little motivation. Why do we want to learn about balanced trees? And then we explain what are balanced trees. In particular, we will be discussing about a special type of balanced tree called AVL tree. We will learn what the words AVL stands for when we get to it. And in discussing about AVL, basically we will be looking at insertion and deletion, because it is after an insertion that a tree needs to be rebalanced, or after a deletion. Now, but before we discuss about insertion and deletion, we will talk briefly about rotations. Rotations are the mechanisms actually that we use to restore the balance of a tree after an insertion or deletion. So that's our target in this lecture. So first of all, motivation about binary balanced trees. As we may have noticed when we discussed about binary search tree last time, sometimes it can be balanced and sometimes it can degenerate into unbalanced, like linked list basically, or somewhere in between. For example, if you try to insert sorted numbers or letters into an BST, for example, if you insert 1, it will obviously go to the root. If you insert 2, it will go to the right of 1. If you insert 3, it is greater than 1, greater than 2, so it's going to go to the right of 3, and so on. So you may end up basically with just a linked list. These are some examples of binary search trees. Clearly the one in C here is basically just a linked list. Now, and then we have B, not too bad, but also not balanced. But A is good, is considered to be balanced. We will explain what balance means technically, what is the definition of a balanced tree in the next slide. Now the problem with unbalanced trees is that their height get tall. And as we remember, the efficiency of searching depends on the height of the tree. We shall explore this idea in a moment. So because of this lack of guarantee of being balanced for BST, that is why we need to learn about balanced trees. These balanced trees, they will have a mechanism to ensure that the tree is always balanced. Okay, so what is a balanced tree? A binary tree is said to be balanced, or if you want the full term, is said to be height balance, if the difference in height of both the left and right subtree is either 0 or 1. So the difference in the height of the left and the height of the right is not more than 1, 0 or 1. For example, if you look at this tree, any node you take, for example 8, its right subtree is of height 1, 2, 3, and its left subtree is of height 1, 2, 3, 4. So the difference is minus 1. We normally take the difference by taking the height of the right, which is 3, minus the height of the left, which is 4. 3 minus 4 is minus 1. And similarly, all the other nodes, none of the nodes goes beyond 1. This one, for example, is plus 1 because the right subtree is of height 1. The left subtree is empty and therefore its height is 0. So 1 minus 0 is plus 1. The leaf nodes, of course, their height is always 0. So there is no left or right. So the difference in height is 0 for all leaf nodes. So once the balance factor once the difference in height is not more than 1, meaning it is minus 1, 0, or 1, then the tree is considered to be balanced. In fact, a tree is said to be perfectly balanced if it is balanced, but also if all the leaves are to be found in 1 or 2 levels. So very similar to the definition of complete tree we discussed before. The leaves must be either in the last level or the level above. So if you have that, plus the fact that it is balanced, then it is said to be a perfectly balanced tree. And this is an example of a perfectly balanced tree. The leaves are either in the last level or 1 level above. In addition to being balanced, and none of the subtrees have the difference in height between the left and right to be above 1. This, however, is not a perfectly balanced, because if you look, the leaves are spread across 3 levels: the last level, second last level, and third last level. So although this is balanced, it is not perfectly balanced. For it to be perfectly balanced, it has to be not only balanced, but the leaves must be found in just the last 2 levels. So that is the definition of balance. Now, what is the advantage of being balanced? To see that, let us take these 2 nice formulas. The first one says the maximum nodes in a binary tree of height h is 2 to the power h minus 1, all minus 1. And the second formula says the maximum number of nodes in 1 level, and usually that is the last level, for a binary tree of height h is 2 to the power h minus 1. Notice that this time minus 1 is with the h. So these are formulas relating the number of nodes in a tree with its height. To see what these formulas mean, let's take some examples. For example, if you have only 1 node, obviously the height is 1. So if you apply the formula to find the total number of nodes, which is the first formula here, 2 to the power 1 is 2, and 2 minus 1 is 1. So obviously there is only 1 node. Similarly, the number of nodes, the maximum number of nodes in 1 level, is given by the second formula. So 2 to the power 1 minus 1. Now 1 minus 1 is 0, and 2 to the power 0 is also 1. So you can see in both cases the formula is true for height 1. There is only 1 node. This is the total. There is also 1 node in the level, in the last level. There is only 1 level, so the formula is true either way. Let's increase our height to 2. So this is our tree. Obviously, the last level has 2. So is our formula correct? 2 to the power 2 minus 1. Well, 2 minus 1 is 1, and 2 to the power 1 is 2. So the formula again is correct. What about the total number of nodes? Is 3. So what is 2 to the power 2, which is 4, minus 1, will definitely also give you the correct number, which is 3. Similarly, for height 3, the maximum in the last level is 4, and the total number is 7. Again, if you try the two formulas, you will see that they are both correct. Here, 2 to the power 3 minus 1, which is 2 to the power 2, is 4. Here, 2 to the power 3 is 8, minus 1, 7, and so on. This is the last example. For height equal to 4, total number 15, maximum in one level, which is the last level, is 8. Now, what is the importance of these formulas? The importance is that if you remember how we search in a binary search tree, we keep going either left or right until we find our target or until we reach an empty tree. Now, the maximum number of comparisons that we have to make in any search is equivalent to the number of the height of the tree. It's equivalent to the height of the tree. This is the maximum. So for example, if you are looking for a node here, then you will have to do 1 comparison, 2 comparison, 3 comparison, 4 comparison. So in 4 comparisons, you will be able to find your node. Okay? Or you'll be able to conclude that it doesn't exist, because the next one is going to give you null. So the point is, if you compare the number of searches you have to do against, for example, what you have to do in the case of linked lists, there is a tremendous advantage here. Here, for a tree that has 15 elements, if they are in a linked list, you may have to search maximum of 15 times before you find your target. Whereas here, the maximum number of search you have to do is 4. So this is really a big advantage. To see this even further, let's take bigger numbers of height, as you can see in this table from the book, figure 6.35. For example, for a tree of height 11, the maximum number of elements you can have is 2047. Now, if you are to search for an element with these numbers in a linked list, in a linked list with this size, you may have to do 2047 searches. Whereas here, the maximum search you have to do is only 11. Okay? And as H increases, the advantage becomes even more. See, for example, when you have height equal to 14, you will only have to do 14 searches against 16,000 searches in a linked list. So this is basically the motivation why we want to use balanced trees to ensure that our searching is very efficient. If you just use ordinary binary search tree, there is no guarantee that it's going to be balanced. So here we are going to learn about a tree that is guaranteed to be balanced, and that is binary search tree. AVL tree, which we are going to learn. So what is AVL tree? By the way, before I continue, I'll just explain the terms AVL. You may be wondering what they mean. It's actually the names of the 3 guys that found the tree: Adelson, Velsky, and Landis. So 3 people who discovered the trees. That's why the tree is named after them, AVL tree. So what does it mean? Here is the definition. An AVL tree is a BST in which the height of the left and the right subtree differ by at most 1. And this is essentially the definition of a balanced tree. So AVL tree is a balanced tree. This is an example, or two examples, one of a balanced tree and one of a non-AVL tree. Here it is AVL because the height is not more than 1. Actually, before we look at it, let's look at the definition of something called balance factor. That will make it easier to know about the difference in the height. Balance factor is defined as the height of the right subtree minus the height of the left subtree. Okay, so not just difference, but the difference in subtracting the height of the left from the height of the right. So here, for example, for note 7, its right subtree is of height 1, 2, and its left subtree is of height 1, 2, 3. So the balance factor is 2 minus 3, height of the right minus height of the left. So these are what these values are actually. They are balance factors of each of the node. So once you see that the balance factors range between -1, 0, and 1, then the tree is considered to be AVL, or balanced tree. Now here is an example of a tree that is non-AVL, because here if you look at tree, its right subtree is empty, so the height of the right subtree is 0, but the height of the left subtree is 1, 2, so 0 minus 2 is obviously -2. Balance factor of -2 or less, or balance factor of 2 and above, are not allowed in an AVL tree. So this is not AVL tree, and therefore is considered not balanced. Okay, now as I said, the way we ensure balanced tree is in the way we do insertion and deletion. After each insertion, we have to make sure that the tree is balanced, and similarly after each deletion, the tree has to be balanced if it becomes unbalanced. And the process of restoring the balance is through what are called rotations. So we're gonna pause about insertion and deletions briefly and discuss about these rotations. What is a rotation? A rotation is a process of switching between children and their parents, so to restore the balance of a tree. This is usually as a result of insertion or deletion. I mean, the tree will become unbalanced after an insertion or deletion, and therefore you will have to do some kind of rotations to restore the balance of the tree. Now when you are doing the rotations, you should concentrate on the deepest unbalanced node. In other words, when a tree becomes unbalanced, there may be many nodes that are unbalanced in that tree. So which of them are you going to restore its balance? The deepest one, the one that is deepest. To see an example, suppose for example we have this AVL tree. It is AVL because all the balance factors are within the range -1, 0, and in fact no one, just 0 and -1. Now suppose you insert 35 in this tree. So 35 is less than 50, so it's going to go to the left, less than 45 and less than 40. So it will end up here. Now if you recalculate the balance factors, you will see that the balance factor of 45 has changed from -1 to -2. because now right is 0, left is 1, 2. But also, if you look at 50, its balance factor has also changed from -1 to -2. Okay, because we have 1 on the right, minus 1, 2, 3. 1 minus 3 is -2. Now, so which of these are you going to do a rotation on to restore the balance of the tree? It is the deepest one. So in this case, 45 is the deepest unbalanced node. It is on this node that you're going to do some rotation. Okay. And what does rotation in this case means? We're going to do what is called left rotation. So left rotation basically means bringing, rotating this 45 to the right. This right rotation, I'm sorry, not left rotation. Rotating this 45 to the right means it's going to go down and its left child will move up. Okay, so that is the rotation. So if you see, this is the result you're going to have. So 45 has moved up, sorry, 40 has moved up and 45 has gone down. So this is called right rotation. We're going to take the different types of rotation one by one and explain each one in detail so that we understand what it means. There are, first of all, two basic kinds of rotation, a right rotation and a left rotation. But actually, when you do an insertion, sometimes you may have to do a double rotation to balance the tree, not just this basic single rotations. So we have what is called double left-right rotation and double right-left and double left-right. We shall see under what situation do we do one of these, either a single right, a single left, double right left, and double left right. Okay, this is the definition of single right rotation. And this diagram also is showing what happens. So in single right rotation, the left child x of a node y. So we have a node y that we need to rotate to the right. Okay, so in right rotation, we have to make x to come up and becomes the parent. Okay, and y to go down and becomes a right child, as you can see here. X has come up, y has gone down to become the right child. Now, but that is right child of x. Y, the parent, has become the right child of x. The question is, what happened to the former right child of x? Because we say y will become the right child of x, but now it may or may not have a right child. Now, if it has a right child, what happens to it? If it has a right child, that right child becomes the left child of y. This is what the next line says. The right child, T2 of x, if any, it may or may not have, but if there is, it becomes the left child of y. So as you can see, T2 has become the left child of y. So this is what is called single right rotation. Single left rotation is similar. We have a node x that we wish to rotate to the left. So as you will guess, y, its right child, will move up to become the parent. Okay, the right child y of x becomes x parent. X will go down to becomes the new left child of y. As you can see, the left child of y is x. So again, you may ask, what becomes of the former left child of y? it becomes the right child of X. It becomes the right child of X. So this is what you have. Okay, this is what the two statements here are saying. X becomes the new left child of Y, and the former left child of Y, T2, becomes, rather the former left child of Y, T2, becomes the right child of X. So this is called single left rotation. What about double right left rotation? It simply means a right rotation followed by a left rotation. However, there is a very important point here. If you are making a double rotation, in this case double right left, the first rotation, which is the right rotation, is not done on the node X that is on balance. Okay, the right rotation is done on its right child. The right child, right? The right child Z is balance. It's not the deepest unbalance. The deepest unbalance is X. So this is the one we want to restore its balance. So we have to do two rotations, a left rotation followed by, a right rotation followed by a left rotation. Now this first rotation, the right one, is not done on the node itself. It is done on the right child. And then finally, the left rotation is done on the node itself. So let us see what happens here. Obviously, rotating Z to the right is, as we explained earlier, is a simple right rotation. So Y will come up to become the parent. Z will become its new right child. Okay, as you can see, and the former right child of Y will become the left of Z. Okay, so this is step number one. Right rotation on the right child of the unbalanced node. And then finally, you rotate the node itself, the node that is not balanced, rotate it to the left. The same definition as we discussed about rotating to the left, meaning Y will come up to become the parent, X will become its left child, the current left child of Y will become the right child of X. So this is the final output you're going to have in a double right left rotation. The double left right is similar. I don't have to go into detail about explaining it. But again, we note that the first rotation, in this case the left rotation, is done on the left child of the unbalanced node, not on the node itself. So we're going to rotate V to the left. So W will go up and you will end up like this. And then you now do the right rotation. So X will go down to become the right of W, and W will become the new root. Right, so these are rotations. We need them in the process of both insertion and deletion. So these are the four cases. Okay, before we look at the cases, let's talk about the insertion now in an AVL tree. The algorithm says insert using the same procedure as BST insertion algorithm. In other words, you start from the top, from the root, keep going left or right until you find an empty slot, then you insert. But after that, now you have to check. And this is for each node. You don't have to wait until you insert 10 elements and then you balance the tree. No, after inserting each node, you have to check if the tree is not balanced, you have to balance it. So after doing the insertion using BST algorithm, now rebalance the tree if an imbalance occurs. And as we explained, an imbalance occurs if a node's balance factor goes out of range. It can go out of range in two ways. Either it was -1 and now it becomes minus 2. Minus 2 is not acceptable. Or it was 1 and now it becomes 2. Either of this will require rebalancing. Now rebalancing, as we said, is done on the deepest unbalanced node. And there are 3 insertion cases. Insertion that does not cause an imbalance. Okay, so in that case, there's nothing to do. The 3 remain balanced, nothing to do. The second case is same side insertion. Either left or right. Either of these require a single rotation. We shall see what this means in a moment. And the final case is opposite side problem, where we have a left-right or a right-left insertion that causes an imbalance. So these are the 2 cases that will require double rotation. To see this, it's better to take examples. So let's start with an example of case number 1. Insertion that doesn't cause an imbalance. Suppose you insert 14 in this AVL tree. So 14 is bigger than 13, but less than 15. So it's going to come to the left of 15. Okay. Now, if you recalculate the balance factors, you will see that they are still within range. Actually, it's only the balance factor of 15 that changes from 1 to 0. Okay, all others remain the same. And therefore, in this case, there is nothing to do. There is no need for rebalancing. Okay, case number 2. Suppose you insert 3 in this AVL tree. You insert 3. So 3 is less than 13, less than 10, less than 5, less than 4. So it's going to go all the way to the left. Now at this point, you try to check, is the tree still balanced? And here I can teach you the best way to know which node is unbalanced, if there is any. Don't start looking from the top, because remember, we are looking for the deepest unbalance. So start from the node that you have just inserted. Obviously that is a leaf node, so its balance factor is 0. So you check, what about the one above? Its balance factor is -1. Why? 0, -1. Right minus left always. Okay, so this is okay. What about 5? Okay, it's right, which is 1, minus left, 1, 2. So 1 minus 2 is -1. So 5 is good. What about 10? 10 is right, which is 1, minus left, which is 1, 2, 3. 1 minus that 3 is -2. So this is not acceptable. So your deepest unbalanced node is 10. Notice if we had started from the top, we will have seen that 13 is unbalanced, because on the right we have 1, 2, on the left we have 1, 2, 3, 4. So you may try to balance the 2, but that is wrong. I mean the 13. You may try to rebalance the 13, but that is wrong, because we should always balance the deepest unbalanced node. Good. Now, after you found the node that is unbalanced, the next question to ask is, what type of unbalance is this? Okay, the way to know what type of unbalance is it is try to move from the unbalanced node towards the new node and count 2 times. See how we are going. Are we going to the left or we are going to the right? In this case, to reach 3 from 10, we will go left, then left, Now, no need to say left again. Count only twice. So left, left. If you see that you are going left, left, then we need a single rotation because this is same side insertion, left, left. Same side insertion require a single left. In fact, same side, left, left, require single right rotation. I have a good summary here summarizing the different insertion. So left, left will require a single right rotation. Similarly, right, right will require a single left rotation. Okay, I have also put in it here, left, left as a problem. The solution is single right. Right, right as a problem. The solution is single left. On the other hand, if you have opposite sides, so you have left, then right, in that case, the solution is left, right. So easy to remember, left, right, left, right. Whereas right, left will require right, left. So these are the 4 cases you can encounter in insertion. Let's go back to our example. So in this case, we said it is a left, left, therefore we need to rotate 10 to the left. So as we learn about, to the right, we need to do a right rotation to the right. Rotate 10 to the right. Rotating 10 to the right, as we remember, simply means 5 will move up, 10 will go down to become its new right subtree. The current right subtree of 5 will become the left of 10. Okay, and this is exactly what we have here. You see 5 has moved up. Now 5 is the left of 13, not 10 anymore. From 13 we go to 5, so 5 has moved up. 10 has gone down to become a right subtree of 5, as you can see here. The new right subtree of 5 is 10. What becomes of the former right subtree of 5? It becomes left subtree of 10. So you can see 8 is now to the left of 10. So this is what is called right rotation. And after doing that, you can see now the tree is balanced. Okay, second example. Suppose we have this tree and we insert 45. 45 will go all the way to the right of 40. So again, if you start from the bottom, so again, after insertion, there are 3 things you have to do. First of all, check if the tree is on balance, starting from the bottom. Okay, 45 being a leaf has balance factor of 0, but 40 has a balance factor of 1, just 1 minus 0, 1. 35 has a balance factor of 1, why? 1, 2 minus 1, so 1. But 30 has a balance factor of 2. Why? The right is 1, 2, 3, the left is 1. So 3 minus 1 is 2. So 30, the root, is in this case the deepest unbalanced node. This is step number 1. Find out if there is an unbalance. Step number 2, you ask yourself, what type of unbalance is this? How to know that? Move from the unbalanced node towards the new node that you just inserted, counting only twice, asking yourself, how am I going? I'm going right and right. So this type of problem is a right problem. Okay, the last question you should ask yourself is, what is the solution for a right problem? The solution is a single left rotation. So we're going to rotate 30 to the left. Okay, so rotating 30 to the left means 35 will move up and replace it at the root. 30 will go down to become its left. As you can see, 35 has gone up, 30 has gone down. Okay, so 30 will become the new left subtree of 35. What becomes of the former left subtree? It becomes the right subtree of 30. So 32 is now on the right of 30. This is how you restore balance in this case. Case number 3 is opposite side, left, right. So if you consider this AVL, now suppose you insert 7. 7 is less than 13, less than 10, but greater than 5, greater than 6. So it will go all the way to the right of 6. Now, as I said, first check, is there a problem? Okay, 7 no problem, 6 no problem, 5 no problem, but 10 has a problem, because the balance factor of 10 is now 2. 1 minus 1, 2, 3. So this is the deepest unbalanced node. Next question is, what type of problem is this? As you move from 10 to 7, counting twice, we will have left or right. So that is the problem. It's a left-right problem. And the last thing is, what is the solution for a right-left problem? The solution for a right-left problem is a right-left double rotation. However, as we recall, in the case of double rotation, the right rotation, sorry, in this case, left, right. So the left rotation, the first one, is done on the left child. So you're going to rotate 5 to the left. Notice that 5 is not unbalanced, it's balanced. Its factor is +1. But in the process of resolving the problem of 10, the first rotation is done on its left child, 5. So we rotate 5 to the left, meaning 6 will move up to replace the 5. 5 will go down to become the left child of 6, as you can see here. Okay. If 6 has a left child, it becomes the right of 5, but in this case it doesn't. So no issue, just move 6 up and 5 will be on its left. So this is step number 1. Now we do the right rotation on the 10 itself. Rotate 10 to the right. This is what we will see in the next slide. No, sorry, here to the left. If you rotate 10 to the right, 16 will move up to replace it, basically, and 10 will go down to become the new right of 6. The current right of 6, which is 7, will be the new left of 10. So this is the final answer that you get. Okay, you have seen 6 has gone up, 10 has gone down to become the new right of 6. The former right of 6, 7, has become the left of 10. Okay, the last example is for the opposite side, but this time requiring right, left. So this is your tree. You insert 15, and 15 will go here to the left of 16. And as its first step, try to see which node becomes unbalanced. It turns out to be 9 is the unbalance. Okay, because 9 has nothing on the left, it has 2 on the right, so it is now +2. Okay, so there is a problem. Next question is, what type of problem? As you move from 9 to 15, you are going right, left. So it requires right, left double rotation. However, the right rotation is done on the right child of 9. The right child of 9 is 16, so rotate it to the right. It simply goes down, 15 will go up to replace it. Okay, that's nothing to do in this case because 15 doesn't have a right child. So just move 15 up and 16 go down. So this is what you have. Step number 1. And the second step, is to do a left rotation on the 9 itself. So if you observe, actually, this first rotation is simply reducing the problem to that of right, so that we can now do a single rotation. Yeah. So so the left rotation is done on 9, and if you do that, 15 will move up to replace the 9. 9 will go down to become its left, and we are done. So these are basically the 4 types of rotations that you will encounter in insertion, and this is the summary of the different conditions that you will encounter and what are their solutions, as I explained earlier. Now, in order to reinforce your understanding of this, I have 2 full examples constructing an AVL tree from a given set of numbers from the scratch. Follow them step by step to see how we do it. So this is our example number 1. We need to insert 9, 7, 2, 15, 20, 11, and 5 into an initially empty AVL tree. So obviously, first we insert 9. 9 will not create any problem, so we can straight away move to the next one. 7 will go to the left of 9, but the tree is still balanced. There is no an imbalance in this case. So we go to 2. Okay, 2 is less than 9, less than 7, and therefore it will end up here to the left of 7. But now if you check, there is a problem with 9, because 2 is fine, 7 is fine, but 9 is having a balance factor of -2. Right, it's 0, -1, 2. Okay, so there is a problem with 9. That's why I mark it here in red. Next question is, what type of problem? Okay, as you move from 9 to 2, you are going left, and therefore the problem is left. Okay, so what is the solution? The solution of left is single right. So we're going to rotate 9 to the right. If you do that, this is what you will end up with. 7 will move up to become the new root. 9 will be to its right. So we are okay. So next we insert 15. 15 will move, will be inserted to the right of 9. It's bigger than 7, bigger than 9, so it's going to go there. Is there a problem? No, because as you can see, obviously 15 has no problem, it's a leaf node. This has no problem. Also 7 has no problem because it is right. 1, 2 minus left, which is 1. So 2 minus 1 is 1. This is good. So go to 20. Notice that if you are doing this manually, because we normally ask this kind of questions in an exam, you should do it exactly as I'm doing. And you don't need to draw a new tree unless if you have to do a rotation. If you have to do a rotation, then you have to draw a new tree to show the result of your rotation. Also, if it is a double rotation that you need to do, you have to draw a new tree to show the result of each of those 2 rotations separately. All right, so having inserted 20, we ask, is there a problem? 20, no problem. 15, no problem, but 9 has a problem, because now 9 is 2 on the right, nothing on the left. Balance factor of 2 is not acceptable. Okay, what is the problem? Right. What is the solution to right? Is single left. All right, so how do you do single left? It means 15 will move up to replace the 9. 9 will go down to become its right child. So this is what you have as your answer. Good. Next, we insert 11. 11 will go to the left of 7, rather right of 7, left of 15, and right of 9. Okay, is there a problem? No problem with 11, no problem with 9, no problem with 15, but there is a problem with 7, because on the right it has height 1, 2, 3, on the left it has 1. 3 minus 1 is 2. So there's a problem with 7. The next question is, what type of problem is this? As you move from 7 towards 11, counting twice, we will have gone right, left. So we have a right-left problem. What is the solution to a right-left problem? It is a right-left double rotation. But the right rotation is done on the right child, and then the left rotation is done on the node itself. Okay, so let us do right rotation on 15. What does that mean? It means 9 will move up to replace the 15, and 15 will go down to become its right child, the right child of 9. What happens to the present right child of 9? It will become the left child of 15. So this is what you end up with. Okay, 9 has gone up. 15 has become its new right. The former right has become the left of 15. This is step number 1. Final step is to rotate 9 to the right. Rotating it to the right means it will move up and become the new root. 7 will go down and become on its left. And that's what we have. Okay, so 9 is the new root, 7 has gone to the left, and that is the result. The final value to insert is 5. 5 will go to the right of 2. And then if you ask yourself, is there an issue? Yes, there is an issue, not with 2, but with 7. Because 7 has nothing on the right, but 2 on the left. So the balance factor is -2. What is the solution, or what type of problem is this? It is a left-right problem. And the solution for left-right problem is left-right double rotation. However, in a left-right double rotation, the left rotation is done on the left child too. And finally, the right rotation is done on the node itself. So if you rotate 2 to the left, basically 5 move up to replace it, and 2 goes to its left. Okay, so this is what you end up after the left rotation. And the last step is to rotate 7 to the right. If you do that, 5 will move up to replace it, 7 will go down to become its right child. So this is the final answer for this problem. Okay, I'll take one more example. Suppose we have a 5, 15, 18, 4, 3, 1, 9, 7, and 12. Maybe this time I'll go a little faster. So inserting 15 up to 18, 15 no issue, but when we put 18 there's an issue, and the issue is with 5. It is a right, so it needs a single left rotation. The result of that is this: 15 will go off, 5 will go to its left. Next we insert 4, no issue so far. Insert 3 and you will have an issue with 5. What is the issue? It is a left problem, and the solution to left problem is a single right rotation. So rotate 5 to the right, and you will have this: 4 going up to replace the 5, 15 going down to become its right child. Insert 1, 1 will go all the way to the left, creating problem with not 3, not 4, but 15. So 15 is the problem. What type of problem? Is left, left. Okay, so what is the solution? Single right on the 15 itself. And how to do that is 4 will now be our root, 15 will be its right. So what happened to its current right? The current right becomes the left of 15. So this is what you have. Okay, inserting 9 will end up there, no issue at all. But when you insert 7, there's an issue with 5. 5 has nothing on the left but 2 on the right. What type of problem? Is right, left. So we need to do 2 rotation. Rotate 9, the right child, to the right, and then 5 to the left. Rotating 9 to the right will give you this. Just 7 will move up to replace the 9, and 9 will go to its right. And then finally, we rotate 5 to the left. So basically, 7 will go up to replace it, and 5 will go down. So this is the solution so far. Inserting 12 will create this, and if you check, no issue with 9, no issue with 7, but there is an issue with 15. It has only 1 on the right and 1, 2, 3 on the left. So there's an issue with 15. What is the issue? It is a left-right. Okay, left-right. As you move from the node that has problem to the new node, counting twice, we have left and right. So that requires left-right double rotation, but the left rotation is on the left child 7, and the right rotation is on the 15. So if we do the left rotation, 9 will move up to replace the 7, and 7 will go down to become its left. Finally, we still need to do the right rotation on 15, and to do that, 9 will move up to replace it. 15 will go down to be its right. Its current right will become the left of 15. So the final answer is this. So I hope with these examples, if you are given a set of numbers to construct an AVL tree, you can do so. Next, we are going to look at the implementation of insertion method.